Welcome back to the deep dive. Today, we are focusing our attention on an organ that is, well, often dismissed as superficial.
It really is. People think it's just a covering.
But it's actually the most extensive and, I think, deceptively complex system in the entire human body. We are, of course, talking about the skin.
It's the body's largest organ, absolutely.
Yeah.
And it's where everything meets the outside world. It's where your barrier function, your immunity, and your personal identity all collide.
Exactly. And for this deep dive, we're going to be synthesizing the conceptual frameworks from two of the definitive texts in the field.
Right. We're looking at what was Chapter 25 in Robinson-Contran Pathologic Basis of Disease and Chapter 24 in Underwood's Pathology.
And our mission here really is to move beyond that sort of cosmetic view of the skin and start treating it as visible medicine.
That's a key phrase from Underwood, and I think it's perfect. In cardiology or hepatology, all the pathology is hidden away. You need imaging, you need blood work to even get a glimpse of it.
Right.
But in dermatology, the pathology is staring you right in the face.
Yeah.
The challenge isn't seeing it, it's learning how to decode it.
And we really need to be explicit about this right up front. This is an interpretive synthesis. We are building a conceptual scaffold, a kind of map to help you navigate the territory. But this is absolutely not a substitute for sitting down with Robbins and with Underwood and actually studying the histology images.
You have to do the reading. Think of this as, the architectural tour before you go and study the blueprints. We want to give you the logic of the building so that when you see the details, they actually stick.
I like that. So let's start with the big picture. Historically, the skin hasn't always gotten the respect it deserves, even in the medical community. I mean, even the great Rudolf Virchow was a little dismissive.
He was. Virchow, the father of cellular pathology, he essentially viewed the skin as a protective wrapper, a covering.
Like it's just there to shield the important stuff inside.
That's exactly it. He saw it as this static covering designed to shield the, quote, more delicate and sophisticated internal organs.
Which is, it's kind of a backhanded compliment, isn't it? Like, you're tough, but you're not very smart.
Exactly. But the modern view, the one that we really get from Robbins and Underwood, is completely different. We now understand the skin as this vibrant, unbelievably complex ecosystem.
It's an active interface.
It's not just a wall. It's more like a border control station. It's got its own military, its own waste management, communications, and sensor array. It's dynamic.
And this brings us to what I think is the central tension of the skin, and it frames basically every disease we're going to discuss today. The skin is trying to do three contradictory things all at the same time.
It's an engineering nightmare, really, when you think about it.
Yeah.
First, at job number one, it has to be a barrier. It has to be tough enough to resist trauma, UV radiation, bacteria. It has to be a suit of armor.
Right. Toughness is job one.
But then, secondly, it has to be incredibly sensitive. It has to be able to detect a fly landing on your arm or, distinguish between a warm cup of coffee and a scalding one.
And a suit of armor is terrible at sensation.
Awful. So it has to be armored, yet it has to be tactile. And then third, it has to be permeable enough to regulate your temperature through sweating. So it's got to let fluid out. But impermeable enough to keep your essential body fluids inside so you don't dehydrate and die.
So it's a barrier, a sensor, and a thermostat all at once.
And almost every single pathology we're going to talk about today represents a failure in balancing those three mandates. Disease happens when those trade-offs just collapse.
Okay, let's get into the architecture of this interface then. Section 1, normal structure and function. And we need to go a bit deeper than just naming the layers. We need to understand the dynamics, or, as Underwood puts it, the bricks and mortar.
Yes, and that analogy is foundational. It's crucial for understanding blistering diseases later on. So the bricks of the wall are the keratinocytes. These are the stratified squamous epithelial cells that make up the epidermis.
But they're not static bricks, are they? They're moving.
They're on a journey. Robbins describes this beautiful vertical migration. It all starts at the very bottom in the basal layer. We call this the mitotic pool.
This is the factory floor.
The factory floor. The cells there are cuboidal, they're active, and they're constantly dividing.
And as new cells are made, they get pushed upward.
Exactly. And as they rise, they differentiate. They start to flatten out. They synthesize this incredibly tough structural protein called keratin. And eventually they go through this programmed cell death where they lose their nuclei.
So by the time they reach the surface,
By the time they get to the top, the stratum corneum, they are essentially just dead, flattened sacks of keratin arranged in what pathologists call a basket weave pattern.
they sacrifice themselves for the barrier.
They do. They give up their vitality to provide that tough outer crust. But, a stack of bricks will just tumble over if you don't have mortar.
And the mortar here is the desmosome.
This is a critical term. Desmosomes are the molecular rivets that hold the keratinocytes tightly together. If you look at them under an electron microscope, they look like little bridges connecting the cells.
And they provide structural integrity against shearing forces. So if I rub my skin, the cells don't just slide apart.
That's the desmosomes doing their job. And structurally, we also need to anchor that whole wall to the ground, right? The epidermis sits on the dermis.
So there's another connection there.
Yes, and the anchors that hold the basal cells down to the basement membrane are called hemidesmosomes.
Half desmosomes.
Essentially, yeah. They connect the cell to the floor, not the cell to its neighbor. Keep that distinction in mind. Desmosomes hold the sheet of cells together. Hemidesmosomes hold the entire sheet down.
And that difference is going to become very important later.
It defines the two major categories of blistering diseases we'll cover. It's all about where the split happens.
Okay, so we have the bricks and the mortar. Now let's talk about the umbrella, the melanocyte.
This is one of the most fascinating cells in the body. The melanocyte sits down in that basal layer, but it looks totally different from the keratinocytes. It's a dendritic cell.
Meaning it has these long arms, these projections.
Exactly. It has these long sort of tentacle-like projections that reach out and weave between the keratinocytes above and around it.
And it's outnumbered, isn't it? The ratio is interesting.
Heavily outnumbered. There's about 1 melanocyte for every 6 to 10 basal cells. But because of those long tentacles, a single melanocyte can service a whole cluster of keratinocytes. We call it an epidermal melanin unit.
And what's it doing? What's its job?
Its job is to synthesize melanin pigment from the amino acid tyrosine via DuPalpa. But here's the amazing part. It doesn't keep the pigment for itself.
It's a philanthropist.
It really is. It packages the melanin into these little granules called melanosomes, and then it physically injects them into the neighboring keratinocytes.
It's literally a delivery service.
It is. And the keratinocytes take that pigment, and they do something incredibly clever with it. They position it specifically over the sunny side of their nucleus.
So it forms a cap.
A literal cap, an umbrella. It's there to shade the cell's DNA from incoming UV radiation, protecting it from mutation.
Yeah.
It's just incredible biological engineering.
It is. And Robbins makes a point here that I think often surprises people regarding race and skin pigmentation.
Right. It disrupts a very common assumption. You might think that darker skin is caused by simply having more melanocytes.
More factories making pigment.
That's not it. The density of melanocytes, the number of factories, is roughly the same across all races.
So what is the difference then?
It's the activity of the factory and the packaging. In darker skin, the melanocytes are producing more melanin, the melanosomes themselves are larger, and they're dispersed more widely within the keratinocyte, and they degrade more slowly. But the number of factories is the same.
That's a fantastic point. Okay, so we have the bricks, the mortar, the umbrella. Who else is in this epidermal neighborhood?
We have the sentry, the Langerhans cell.
The immune spy.
Exactly. These are dendritic antigen-presenting cells that reside in the epidermis. They are the outpost guards of the immune system. Their job is to constantly sample the environment.
Looking for trouble.
Looking for trouble. They capture antigens, say a protein from a virus or an allergen like the oil from poison ivy, and then they physically migrate out of the skin, travel to the local lymph nodes, and present that evidence to the T cells.
They're saying, hey, look what I found on the perimeter.
And that's what initiates the adaptive immune response. Finally, we have the Merkel cell, also down in the basal layer.
The mystery cell.
Robbins literally calls them that. They are neuroendocrine cells, and we know they're involved in mechanoreception, probably sensing light touch, but their full function is still being mapped out.
So that covers the epidermis, this whole complex dynamic layer. But all of this sits on a foundation, the dermis.
Right. If the epidermis is the wallpaper and the paint, the dermis is the drywall and the studs. It provides all the mechanical support, the plumbing, the wiring. It's connective tissue.
And what are the key components here? What gives it that strength?
2 main proteins, collagen and elastin. Collagen provides tensile strength. It's what prevents your skin from tearing when you pull on it. Think of it like rebar in concrete.
And elastin.
Elastin provides recoil. It's like a rubber band. It allows the skin to snap back into shape after being stretched. As we age, we lose both, which is why skin sags and wrinkles.
And Underwood mentions the specific orientation of these fibers, Langer's lines. Why is that important?
This is absolutely crucial for surgeons. It turns out the collagen fibers aren't just randomly arranged. They run in specific, predictable patterns across the body, like the grain in a piece of wood.
So a surgeon needs to know the grain.
They have to. If a surgeon makes an incision parallel to these lines, the wound edges stay naturally approximated, and it heals with a fine, thin scar. But if they cut across Langer's lines, the tension from the collagen fibers pulls the wound open, leading to a wide, ugly scar.
So just knowing the grain of the dermis can completely change the cosmetic outcome of a procedure.
Absolutely, it's fundamental.
Okay, finally, in this architecture section, we have to talk about the holes in the armor, the annexa.
Right, the hair follicles, sebaceous glands, and sweat glands. What's interesting is that these are actually invaginations of the epidermis that push down deep into the dermis.
And they're obviously vital for things like thermoregulation and keeping the skin lubricated with sebum.
Yes, sebum has antimicrobial properties too. But you're right to call them holes. They are vulnerabilities.
They're designed in weak points.
They are breaches in the castle wall. A hair follicle is basically a tunnel that bacteria can use to bypass the entire stratum corneum and get deep into the tissue. That's why we get things like folliculitis or furuncles boils. It's the price we pay for having hair and sweat.
Okay, that sets the stage perfectly. We have the structure.
Yeah.
Now let's move to section 2, the language of dermatology.
Yes, this is where that visible medicine concept really comes into play. Dermatology has its own unique syntax. When we look at a rash, we use these clinical descriptive terms, but every single one of those terms translates directly to a specific pathological process.
So we're decoding the visual signs. Let's start with a really common one, scaling. We see dry, flaky skin. What is happening at the cellular level?
Pathologically, scaling corresponds to a process called parakeratosis.
And what exactly is parakeratosis?
Well, remember we said that normally the keratinocytes lose their nuclei as they reach the surface.
Right, they become enucleated bags of keratin.
In parakeratosis, for some reason, the nuclei are retained in the stratum corneum. You can see them on the slide.
Why would they keep their nuclei?
Because a factory is rushing. The cell turnover is too fast. The cells are being pushed to the surface before they've had time to fully mature and go through that final step of degrading their nuclei. So when you see scale, you should immediately think accelerated cell turnover.
Got it. Okay, what about spongiosis? That's a very descriptive term.
It is, and it looks exactly like it sounds, a wet sponge. Spongiosis is intercellular edema. It's fluid accumulating between the keratinocytes and the epidermis.
And where is that fluid coming from?
It's leaking from inflamed blood vessels down in the dermis. The fluid leaks out, pushes up into the epidermis, and literally splays the cells apart. It stretches those desmosomes, those little rivets, really tight.
And if it stretches them too far?
They break. The fluid then pools together, and you form a vesicle or a blister. This is the absolute hallmark of eczema. So when you see a wet, weeping, or blistering rash, your first thought should be spongiosis.
Okay, another one, acanthosis.
That's just a fancy term for epidermal hyperplasia. The epidermis gets thicker. It's usually a response to some kind of chronic irritation like rubbing or scratching or chronic inflammation.
So the skin is building up its defenses.
Exactly. It's making the wall thicker.
And finally, just for basic description, let's distinguish between a macule, a papule, and a nodule.
It's all about depth and elevation. A macule is flat. It's a change in color only. You can't feel it with your eyes closed. Think of a freckle.
Okay.
A papule is raised and small, usually less than a centimeter. You can feel it. A common mole is often a papule. A nodule is also raised, but it has significant depth. It feels like a marble under the skin.
So knowing that vocabulary allows us to speak the language. Now let's use it. Let's enter section 3, disorders of inflammation, the immune battlefield.
This is a huge and really important category of skin disease. Robbins divides them into acute and chronic, which I think is a very useful framework.
Let's start with the acute. Everyone knows urticaria, or hives.
Hives are the classic immediate type I hypersensitivity reaction. The key player here is the mast cell in the dermis.
And what triggers it?
It can be an allergen pollen, certain foods, drugs, or even just physical pressure or cold. The trigger causes the mast cells to degranulate, which means they just dump a massive amount of histamine into the surrounding dermis.
And histamine causes?
Vasodilation and increased vascular permeability. The small blood vessels become leaky. Fluid rushes out into the dermis, importantly, not the epidermis, and that's what causes those puffy, red, incredibly itchy plaques we call wheals.
And they happen fast and they go away fast.
Yep, often within hours. Contrast that with acute eczematous dermatitis eczema.
The completely different mechanism.
Completely different. Eczema is a type IV hypersensitivity reaction. It is T-cell mediated. This is a delayed response, not an immediate one.
So walk us through the mechanism. Let's say I touch poison ivy.
Okay. The antigen, the oil from the plant, touches your skin. The Langerhans cells, our little spies, capture it. They then run to the lymph nodes and present it to CD4 positive T cells. Those T cells become sensitized.
They memorize the enemy.
Exactly. Nothing happens on first contact. But then, upon re-exposure, those now sensitized T cells migrate back to the site of contact in the skin, and they release a flood of inflammatory cytokines.
And those cytokines are what cause the rash.
They're what cause the damage. They damage the keratinocytes directly, and they make the dermal vessels leaky. That's what leads to the spongiosis we just talked about.
The fluid seeps into the epidermis.
Exactly. The fluid separates the cells, stretches the desmosomes, and forms vesicles. That's why acute poison ivy is classically blistering and wet and oozing.
But what happens if that eczema becomes chronic? If someone keeps scratching the same spot for months?
The whole morphology changes. The oozing and blistering stops. The skin dries out. It thickens and it gets scaly. You get acanthosis, that epidermal thickening, and hyperkeratosis, which is a thickened stratum corneum. Clinically, we call this lichenification.
It starts to look like tree bark.
Yes. It's the skin basically saying, if you're going to keep attacking me and scratching me, I'm just going to build a thicker wall. It's an adaptive but ultimately pathological response.
There's one more acute one I want to cover, erythema multiforme. This one has a very specific, almost iconic look.
The target lesion. It literally looks like a bullseye or a target.
What's the mechanism there? It's not spongiosis, is it?
No, it's totally different. This is a cytotoxic attack. CD8 positive cytotoxic T cells specifically target and kill the basal cells of the epidermis.
Why are they doing that?
It's usually triggered by an underlying infection, most commonly herpes simplex virus or mycoplasma pneumonia, or sometimes certain drugs. The theory is that fragments of the virus or drug get stuck to the basal cells, and the immune system sees those cells as foreign and attacks them.
It's trying to kill the infected cells, but it's causing collateral damage.
Massive collateral damage. Histologically, you see what's called an interface dermatitis. You see a line of lymphocytes attacking the junction between the dermis and epidermis. And you see these dead, necrotic, pink basal cells, which pathologists call civet bodies.
Civet bodies. Good name for a band.
A death metal band, maybe.
Okay, let's shift gears to chronic inflammatory dermatosis. And the big one here, the one everyone thinks of, is psoriasis.
Psoriasis is just a masterclass in immune signaling gone wrong. It affects 1 to 2% of the population, and it's so much more than just a skin condition. It's a systemic inflammatory state that's linked to arthritis, heart disease, and depression.
And Robbins really identifies the specific immune pathway involved now.
Yes, and this is crucial because it's led to the development of modern biologic drugs. It's a T-cell mediated autoimmune reaction that centrally involves the Th1 and Th17 pathways.
It's a cytokine soup.
It is. A soup made of things like IL-12, IL-23, IL-17, and TNF-alpha. And this soup sends a powerful, unrelenting signal to the keratinocytes in the epidermis.
And that signal is
Grow. Grow now. And do not stop.
how fast are we talking?
Normally, it takes about 28 days for a keratinocyte to go from the basal layer to being shed from the surface. In a psoriatic plaque, that entire cycle is compressed to just 3 to 4 days.
That is just absurdly fast.
It's out of control. And this leads to a profound acanthosis, that thickening of the epidermis. But it's a very specific pattern of thickening. The rete ridges, the downward projections of the epidermis, elongate downward uniformly. Robbins describes them as looking like test tubes in a rack.
And because the cells are rushing to the surface so quickly, they don't have time to lose their nuclei.
So you get massive perikeratosis.
Yeah.
And that retained nuclear materials are what creates that classic silvery white scale that you could just scrape off.
You also see something else in the microscope, right? Little pockets of pus.
Yes. For some reason, neutrophils are attracted up into the stratum corneum, where they form these little collections, these little microabscesses called Monroe microabscesses.
And clinically, there are a couple of famous signs associated with psoriasis.
Yes. The first is the Auspitz sign. This is when you scrape off that silvery scale and you get pinpoint bleeding points underneath.
Why does that happen?
It's because as the epidermis thickens downward, the dermal papillae, which contain the superficial blood vessels, get stretched thin and pulled upward, very close to the surface.
Yeah.
So when you peel off the scale, you're literally ripping the roof off those dilated, fragile vessels.
And the second sign is the Koebner phenomenon.
This is fascinating. This is where new psoriatic lesions form at sites of local trauma. If a patient with psoriasis gets a cut or even just scratches their arm, a new linear plaque of psoriasis will often form right along the line of the scratch.
It's a self-fulfilling prophecy of inflammation. The trauma attracts the inflammatory cells, which then start that whole cytokine loop all over again.
Precisely.
Before we leave inflammation, let's just briefly touch on lichen planus.
The disorder of the PS. Pruritic, purple, polygonal, planar pupillae.
And the histology is very distinct from psoriasis.
Very. Instead of those rounded test tube ridges, in lichen planus you see a jagged sawtooth pattern at the dermo-epidermal junction. The inflammation, which is a dense, band-like infiltrate of lymphocytes, is specifically destroying the basal layer, causing it to collapse in this jagged pattern.
Okay, so that's inflammation. Now let's move to section 4, blistering diseases. This is where, for me, structural biology meets pathology in the most elegant way.
I love this section because it is so logical. It's pure mechanics. Blisters form where the structural glue of the skin fails. If you know where the glue is supposed to be, you can diagnose the disease.
And we already established the key difference between desmosomes, which are cell-to-cell, and hemidesmosomes, which are cell-to-floor. So let's apply that. Start with pemphigus.
Pemphigus, specifically pemphigus vulgaris, is an autoimmune attack on the desmosomes. The autoantibodies target a protein called desmoglein.
So the bricks are losing their mortar.
And they simply fall apart from each other. The medical term for this is acantholysis. The cells round up and just float away from each other within a fluid-filled space.
So where is the split, the blister, located?
Since desmosomes are everywhere between the cells, the split happens inside the epidermis, usually just above the basal layer, which remains attached to the floor. We call it a suprabasal split.
And because the roof of that blister is just a few thin layers of cells.
It is incredibly fragile. These are flaccid bullae. They rupture almost immediately. You very rarely see an intact blister in a patient with pemphigus. What you see are painful, crusted erosions, very often starting in the mouth.
Okay, now diagnostically, if we do immunofluorescence, if we stain the tissue to see where the antibodies are, what pattern do we see?
You see a classic fishnet pattern. Since the desmosomes surround each and every keratinocyte, the green fluorescent stain outlines every single cell. It looks like a net cast over the tissue.
Okay. Now let's contrast all that with bullous pemphigoid.
So in bullous pemphigoid, the autoantibodies are targeting something different. They're going after the hemidesmosomes, specifically a protein called BPAG2, right at the basement membrane zone.
So the attack isn't between the cells, it's at the floor.
Exactly. The entire epidermis lifts cleanly off the dermis as a single intact sheet. The split is subepidermal,
Which means the roof of the blister is the full thickness of the epidermis.
making it incredibly strong and resilient. These are tense bullae. They don't rupture easily. You can have these large, intact, fluid-filled blisters all over the skin.
And the immunofluorescence pattern.
Since the target is the basement membrane, which is a thin line, you see a smooth, linear band of IgG deposited right along the bottom of the epidermis, a straight green line.
So let me recap. Pemphigus equals desmosomes, an intraepidermal split, a fishnet pattern, and fragile blisters.
Correct.
Pemphigoid equals hemidesmosomes, a subepidermal split, a linear pattern, and tense blisters.
That is the high-yield summary that you absolutely have to know.
There's one more blistering condition that Robbins highlights, which has this fascinating systemic connection, dermatitis herpetiformis.
Yes. This is the skin manifestation of celiac disease.
Gluten sensitivity.
Right. What happens is the patient makes IgA antibodies against gluten in their gut. For reasons we don't fully understand, these antibodies cross-react with reticulin fibers in the skin, and they get deposited in a very specific location.
Where's that?
At the very tips of the dermal papillae. Just the tips. This attracts a swarm of neutrophils, which form these tiny microabscesses and cause the epidermis to lift off right at those points.
And that results in?
Intensely itchy group vesicles, often on the elbows, knees, and buttocks. It's called herpetiformis because they look like herpes,
Right.
but it has nothing to do with the virus.
So the skin is literally blistering because of what the gut is eating.
Exactly. And if you treat the diet, put the patient on a strict gluten-free diet, you often completely clear the skin. It's a beautiful example of a systemic disease presenting on the skin.
Now, here is a moment of synthesis that just blew my mind when I was reading this section. It's the connection between an autoimmune disease, pemphigus, and a common bacterial infection, impetigo.
This is the comparative pathology aha moment. So we just established that a form of pemphigus, called pemphigus foliaceus, is caused by an autoantibody that specifically attacks desmoglein 1, a desmosome protein in the upper epidermis.
Right. A superficial split.
Well, it turns out that bullous impetigo, which is caused by Staphylococcus aureus, is caused by a bacterial exotoxin that specifically seeks out and cleaves desmoglein 1.
No way. So the bacteria evolved a weapon that targets the exact same structural protein that the autoimmune disease targets.
Precisely. It's a completely different cause.
Uh-huh.
A bacterial toxin versus an autoantibody.
Yeah.
But they hit the exact same target, desmoglein 1, and produce a very similar result,
Oh.
a superficial subcorneal blister.
Yeah.
It's just incredible convergent pathology.
That leads us perfectly into Section 5, infections, the barrier breaches.
The skin is a fortress, but it is constantly under siege from bacteria, viruses, and fungi.
Let's start with that same bug, impetigo. We see this in kids all the time.
The classic honey-colored crust, it's usually Staph aureus or Strep pyogenes. It's a very superficial infection. You see a collection of neutrophils accumulating just beneath the stratum corneum.
And it usually doesn't scar, right?
No, because it doesn't violate the dermis. The damage is all contained within the epidermis, which would regenerate perfectly. It stays in the attic.
Okay, what about viral infections? Let's talk about warts.
Verrucae. These are caused by the human papillomavirus, or HPV. The virus infects the keratinocytes and hijacks their cellular machinery to replicate itself.
And it leaves a very specific fingerprint on the cell.
It does. Histologically, the pathognomonic finding is coelcytosis.
Can you describe that? What does a coelocyte look like?
It's a keratinocyte with a dark, shrunken, raisin-like nucleus, and it's surrounded by a clear halo. That clear halo represents the cytoplasmic clearing caused by the viral cytopathic effect. If you see coelocytes, you are looking at an HPV infection.
And another common viral one, molluscum contagiosum, a pox virus.
Another viral hijacker. This one is famous for creating these massive pink eosinophilic cytoplasmic inclusions called molluscum bodies. They're so large they push the nucleus of the cell off to the side. Under the microscope, they are completely unmistakable.
Let's talk fungal, tinea, wingworm.
Which, of course, is not a worm at all. It's a dermatophyte fungus.
And the interesting thing here is where the fungus actually lives.
It lives exclusively in the dead keratinized layer, the stratum corneum. It eats dead keratin. That's its food source. It generally doesn't invade the living tissue below.
So if the fungus is just on the surface, why does it look so red and angry and inflamed?
That's the host response. Your immune system senses the metabolic byproducts of the fungus and launches a mild inflammatory attack against it. That's what creates the red scaly ring at the advancing edge of the infection. The fungus is just grazing on the pasture. The redness is us trying to burn the pasture down to get rid of it.
And if we need to confirm it's a fungus?
We do a biopsy and use a special stain called a PAS, stain periodic acid Schiff. The fungal hyphae will turn a bright magenta or red color, making them easy to see against the blue background.
All right. Section 6. Disorders of pigmentation and melanocytes. This is where, personal identity and some very high-stakes pathology really meet.
Absolutely. Everyone looks at their moles. It's probably the most common reason for a dermatologic consult. Doc, is this spot dangerous?
So let's clarify some basic terms first. What is the difference between a freckle and a lentigo?
To the naked eye, they can both just look like small brown spots. But pathologically, they're essentially opposites. A freckle, or an ephilus, has a completely normal number of melanocytes in the basal layer.
But it's dark. Why?
Because the existing factories, the melanocytes, are working overtime. They are overproducing melanin in response to sun exposure. And crucially, freckles darken in the summer and fade in the winter. They are cyclic.
And a lentigo?
A lentigo is an actual hyperplasia. There is an increased number of melanocytes. You see them lined up like soldiers along the basal layer. And because it's a structural change, they do not fade in the winter. They are stable.
Okay, that's a key distinction. Now let's talk about nevi, or moles. Robbins outlines a kind of life cycle for the common mole.
Yes, and this is a great concept. Moles age, just like we do. They typically start as junctional nevi.
Meaning the nests of melanocytes are located right at the junction between the epidermis and the dermis.
Exactly. And at this stage, they're usually flat and dark, brown or black. Over time, those nests of cells begin to migrate down into the dermis. Now you have nests at the junction A and D in the dermis.
That's a compound nevus.
Right. And because there's now a dermal component, the mole becomes raised. And finally, as it continues to age, the junctional component can disappear entirely. All the nests are now deep in the dermis. This is an intradermal nevus.
And these are those fleshy, often pale, dome-shaped moles you see on older adults?
Exactly. And what's interesting is that as the cells migrate deeper, they tend to produce less pigment. They mature. But most importantly, at some point, they stop growing. They enter a state called oncogene-induced senescence.
The brake pedal gets pressed.
That's the perfect analogy. An early mutation, often in a gene called BRAF, steps on the gas pedal. But the cell's internal safety mechanisms, like a protein called P16, slam on the brakes. The mole exists, but it just sits there. It sleeps.
But sometimes the brakes fail, or the gas pedal gets stuck to the floor. And that's when we get melanoma.
The monster. Melanoma is a malignant tumor of melanocytes. And to understand it, we have to talk about genetics and, crucially, geometry.
Okay, let's start with the geometry, the growth phases.
This is the single most critical concept for prognosis in melanoma. Early on, most melanomas are in the radial growth phase. This means the malignant cells are spreading horizontally or radially within the epidermis and maybe the very superficial dermis.
Like an oil slick spreading on top of the water.
Perfect analogy. And here's the key. The epidermis has no blood vessels and no lymphatics. So as long as the tumor stays in that radial growth phase, it physically cannot metastasize.
It's trapped.
It is trapped. If you catch it at this stage and cut it out, the cure rate is essentially 100%. But eventually, a switch flips. The cells acquire the ability to invade downward. This is the vertical growth phase.
They breach the basement membrane and invade the deep dermis.
And once they're in the dermis, they have access to the highway system, the blood vessels, and the lymphatics. From there, they can travel anywhere. The lymph nodes, the brain, the liver, the lungs.
And this leads directly to the most important prognostic factor of them all, Breslow thickness.
It is a literal measurement of depth. A pathologist uses a micrometer in the microscope to measure from the top of the granular layer of the epidermis down to the deepest invasive tumor cell in millimeters.
So it's not how wide the mole is, it's how deep the iceberg goes.
That's it. A melanoma that is less than, say, 0.75 millimeters deep has an excellent prognosis. One that's greater than 4 millimeters deep has a very poor prognosis. Depth equals danger.
And Robbins dives into the genetics here. It's not just sun exposure.
Sun is the environmental trigger that causes the DNA damage, but the engine of the cancer is often a specific mutation in a signaling pathway, most commonly in genes like BRAF or RAS.
And BRAF mutations are found in, what, 40 to 50% of melanomas?
Yes, specifically the V600E mutation. This is a signaling kinase that gets permanently stuck in the on-sem position. It's constantly telling the cell to divide and survive no matter what.
And this matters because we now have drugs that can target that.
We do. We have BRAF inhibitors like vimurafenib. They can produce dramatic, albeit often temporary, remissions in patients with metastatic melanoma. Understanding that pathway has revolutionized treatment.
Let's finish up with Section 7, epithelial tumors. This is the price of aging and a lifetime of UV exposure.
Right, and we have to start with the benign but incredibly common barnacles of aging, the seborrheic keratosis.
The ones with that stuck-on appearance.
Exactly. They look waxy, coin-like, almost like someone dripped brown candle wax on the skin. You feel like you could just peel them off. Histologically, they're benign sheaths of basiloid cells with these little swirls of keratin called horn cysts.
They're harmless, usually.
Almost always. The one exception is when you see the sign of Lézard-Trélat.
What is that?
This is a rare paraneoplastic sign. If a patient suddenly, over a few weeks, erupts with hundreds of these seborrheic keratoses all at once, it can be a signal that there is an underlying internal malignancy, most commonly a GI adenocarcinoma, that is pumping out growth factors like TGF-alpha that are making the skin go crazy.
Visible medicine again. The skin is shouting about a problem in the stomach.
That's it, exactly.
Okay, what about actinic keratosis?
These are those rough, gritty, sandpaper-like patches you feel on sun-exposed skin, like the face and the back of the hands. These are pre-malignant.
So they are the waiting room for cancer.
That's a good way to put it. They represent dysplasia, or atypical cells, in the lower levels of the epidermis. They are full of P53 mutations caused by UV damage. If left untreated, a certain percentage of them will evolve into a full-blown squamous cell carcinoma.
And that's squamous cell carcinoma, SCC.
This is a fully malignant tumor. The dysplasia now involves the full thickness of the epidermis, and the cells have invaded down into the dermis.
And even though they're malignant, the cells still try to do what they remember doing.
They do. They remember they are squamous cells, so they try to make keratin, but they do it poorly and in the wrong place, deep in the dermis. And you see these characteristic keratin pearls, whirls and swirls of pink keratin trapped in the dermis.
And can it metastasize?
It can, though it's much less common for a cutaneous SCC to metastasize than, say, an SCC in the mouth or esophagus, but it is locally invasive and can be destructive.
And finally, the most common invasive cancer in humans, period, basal cell carcinoma, BCC.
The rodent ulcer.
Why that nickname, rodent ulcer?
Because if it's left untreated, it just slowly and relentlessly gnaws away at the tissue, creating a disfiguring, ulcerated crater. But here's the paradox. It almost never metastasizes.
So it digs in deep, but it doesn't travel.
Correct. And the genetics here are very distinct. Basal cell carcinoma is driven by mutations in the hedgehog signaling pathway.
Like the video game character Sonic Hedgehog.
That's the one. Specifically, mutations in a tumor suppressor gene called PTCH1 lead to uninhibited constant hedgehog signaling, which drives the proliferation of the basal cells.
And the histology is classic, right?
Absolutely classic. You see these nests of dark blue basaloid cells dropping down into the dermis. And if you look at the very edge of the nest, the cells line up perfectly parallel to each other like a picket fence.
Palisading.
Peripheral palisading. And often, the stroma around the tumor pulls away during processing, creating this little artifactual cleft or white space. If you see nests of blue cells with palisading and clefting, it is a basal cell carcinoma.
Wow, we have traversed the entire landscape, from the molecular rivets of the desmosome to the cytokine storms of psoriasis and the deep invasion of melanoma.
It really brings us back to that initial mission statement. The skin is the ultimate interface. It's a living record of your genetics, your immune status, and your entire history of environmental exposure.
So synthesizing all of this, what are the big overarching takeaways?
I think there are three. One, the skin is an immune organ, first and foremost. Inflammation is a disorder of signaling, not just simple irritation. Two, structure dictates pathology. Knowing the difference between a desmosome and a hemasmosome is the key to understanding why pemphigus is fragile and pemphigoid is tense.
And three, depth determines destiny.
Especially in neoplasia. The radial growth phase is your window of opportunity for a cure. The vertical growth phase is the danger zone.
I want to leave our listeners with one final provocative thought that Robbins just touches on, but we could do an entire separate deep dive on it. The microbiome.
Yes. We've spent this whole time talking about infections as invaders. But our skin is covered in what is essentially a zoo of commensal bacteria and other organisms.
We're not an individual, we're an ecosystem.
We absolutely are. And those good bacteria like Staph epidermidis, Cutibacterium, they occupy all the available niches so the bad guys can't get a foothold. They also help prime and educate our immune system.
So the question is, in our modern quest for hyperhygiene, all the scrubbing, sanitizing, antibacterial soaps, are we actually damaging our own first line of defense?
It's the hygiene hypothesis applied to the skin. By constantly stripping the barrier and killing off our commensal partners, we might be creating a state of dysregulation that actually makes us more prone to allergy and infection. We might be leaving the castle gates wide open.
Something to think about next time you reach for the antibacterial soap.
Indeed.
A final call to action for our listeners, then. We've built the map for you. Now you need to go and walk the territory yourselves.
Open Robbins to the skin chapter. Open Underwood. Go look at the photomicrograph of a keratin pearl, an SCC. Find the image of the sawtooth ridges in lichen planus.
We can describe the fishnet immunofluorescence pattern of pemphigus all day, but until you see that green glowing image for yourself, it won't be burned into your retina.
This deep dive is the scaffold. The textbook is the building.
Go do the work. Thanks for listening to The Deep Dive.
See you next time.